So in our last video, we calculated a process CP and CPK to start to understand how what we were doing was meeting our expectations. Very generic way of saying it. We're going to go one step further in this video by saying we can now calculate an expected PPM. And the reason for this is if we say to somebody, our process capability equals 0.387, right? We talked about that is not, it is an indication that our process is not functioning well, all right? But it's not very clear. What we can do, though, another way to explain this is we can say, all right, we can calculate an expected PPM. And many of us know PPM is an industry standard in a number of different industries. It's basically, it stands for parts per million. We're basically, in our case, going to go in and we're going to calculate some percentage of values, right? And we're literally going to multiply them that value times 1 million. That's going to give us our PPM. And the reason why different industries use PPM is basically we can take very small decimals, and then when we multiply them by 1 million, it literally will be going in. It's like putting a magnifying glass on those numbers. We can take small decimals, and they turn into much larger whole numbers. Right? It's literally just a way to take these, shine a light on what's going on. Right. So if we look at this expected PPM calculation, in our last example, what was given to us was we had a process. It was under statistical control. Our upper specification limit was 40. Our lower specification limit was equal to 30. Our X bar was equal to 36. We had a sample in addition to that. X bar was 36. Our sample size was 32. And our sample standard deviation was 3.45. Okay. So that was our given information, the problem that we just had looked at, which resulted in kind of this low CPK value. So if we want to look at this as an expected PPM, ultimately this is the number that we're looking for. All right. What we can say is we've got our process here. In the example, we said it's normally distributed. All right. And what we can do now is if this is where my lower specification limit is, and this is where my upper specification is, what we can do is convert these to a familiar number. We can convert these to a z-value, a standard normal value, all right? So to look at a standard normal value for this lower specification number, we're going to say our lower specification limit minus our X bar divided by our standard deviation. Correspondingly, we can find a z-value for our upper specification limit minus our X bar divided by our standard deviation. This is very familiar. This goes all the way back to when we started looking at normal distributions. All right, and we had the z-value is basically some value of x minus the mean divided by the standard deviation. All right, then we involved the central limit theorem and we started using samples. All right, and we started recalculating our z-values slightly differently because we had the sample standard or the standard error of the mean. All right, so we look at this z-value for the lower specification limit now. We've got 30 minus our 36 divided by 3.45. Our z-value for our upper specification limit now is 40 minus 36 divided by 3.45. It tells us then that this z-value for our lower specification limit ends up being negative 0.174. All right, that is my calculated value. Over here, my calculated value for my upper specification limit ends up being positive 1.16. What we can then do is use these z-values to find these areas in the normal distribution, and then we can find the areas to the extreme of those. We're then going to add those up, multiply times 1 million to find our PPM. And again, literally graphically here, we're saying anything below this value results in a problem. Anything above this value results in a problem. So if we look at our z-distribution table for a negative 1.74 gets us to an area of 0.4591. Correspondingly, if we look at a z-value for the positive 1.16, our z-value ends up being 0.3770. Remember, this distribution is symmetrical. If we take this value from 50%, it tells you that this area, we're just going to call this area sub 1. Area sub 1 which is the value to the extreme of this, is 0.3770 from 0.5. It tells us that area 1 is 0.123. This area 2 over here is 0.5 minus the 0.4591. Area 2 ends up being 0.0409, right? Our ppm is represented in both of these extremes, so we've got to add those up. 0.1639. Basically what this is saying is 16.4% of everything we're doing is a problem. We don't really have to multiply this times 1,000,000 to see that, but if we want to complete that, we're going to say, all right, our percentage now is 0.1639, right, times my 1,000,000. Tells me my PPK is 163,900. Right? That's the value that we're looking for. You don't have to dig far and by doing some independent research to find that that is a wholly unacceptable value in pretty much any application. And you look at especially different complex processes and manufacturing. A lot of times you're going to see a very low limit on the ppm because you have complex products that involve a lot of different parts and pieces. And so even if you're making something very simple, by the time you put it together in a really complex thing like a car, all right, we have to be careful that the overall vehicle build that you would have put together is going to be not good. It's not going to be a high quality product. You could also imagine if we have really detailed services that we provide and you're just a small part of a larger service to a customer, if all of the inputs are really poorly run and the data indicates that, by the time you get to the end item with the customer, you're going to have some very unhappy customers. All right. But in terms of the calculation of ppm, it's a relatively simple calculation. Don't be overwhelmed by it. We're following kind of the standard path. We're writing out our given information. We're relying on some past theories directly that we're leveraging. So there's really a lot of new, really there's nothing new here, but we're relying on familiar things that we've been doing over the last few weeks. And we're just applying it into a new and really practical kind of way. So that's a good summary, I hope, of how you would go about calculating parts per million in the context of a capability study.